The next couple of videos are going to illustrate how to actually carry out a mediation analysis procedure in R. But before getting to that, I want to first introduce you to the hypothetical data again, and also revisit what mediation analysis is actually doing. The packages that I'm planning to use in this series of videos are boot, Lavon, and mediation, all of which come from the Comprehensive R Archive Network CRAN, so we can install them the usual way. I've done so before recording, and retrieve the functions in them for use in our current R session using the library function the way that we normally do. Then I also want to use the function process made by Andrew Hayes. And this function is available on Andrew Hayes' website, processmacro.org. It is not in a package on CRAN. So I've retrieved the file process.r from the website and placed it in my working directory so I can call the source function with the string representing that file name as its argument and execute all of the code contained within that file. And that makes the process function available for later use. The next step is to set up the hypothetical data that I'm going to use for all of the examples today. And this is a familiar data set, robots, that you can create by running the makerobots.r code file that's also provided with this video series. And this should be a familiar example to you if you watched my earlier videos illustrating the conceptual basis and practical applications of linear regression analysis. You can watch the first video in the Regression Demos video series for a reintroduction to the robots dataset. The basic idea is that each participant evaluated a robot and decided how much they would be willing to pay for it, represented in the price variable. And the researchers are interested in the ways that various features the robots have, such as having legs or wheels, might influence participants' evaluations of how much that they would be willing to pay for the robot. In order to get ready to use this data set for today's examples, I'm going to do a couple of additional things to it. First, I'm going to set the reference category for the transport factor to wheels for convenience, because I would like to test questions about how much more expensive robots with legs are compared to robots with wheels. And I'm also just going to create a new variable called legs. That's a binary variable where 0 represents robots with wheels and 1 represents robots with legs. The reason I'm not going to use the factor in every case is that the usual structural equation modeling tools don't work well with factors. So this dummy variable is going to take the place of the transport factor in some of the analysis. Several of the tools that I'm going to use for statistical mediation analysis today are built on structural equation modeling, but this class isn't going to cover structural equation modeling in any more detail than the examples from today. You can always take a separate class on that topic. For all of the procedures in the examples today, we want all of the models to use the same subset of data, and having different variables in the data set with different missing values can create a situation where when we fit models on all available data, the sample size depends on which variables we're including. To avoid the challenges created by this situation, I'm just going to remove the 50 cases in this hypothetical data set that have any missing values in the data frame, leaving a sample size of 500. If you were preparing your own data set for analysis procedures like the ones I'm going to show today, it would make sense to only remove cases with missing values on the variables that you plan to use in your analysis, not the entire data set. In this case, I happen to know that those are the same set of 50 participants who have missing values on the variables of interest. So what I've done is I've used the square brackets to retrieve a subset of the robot's data frame where the rows have a value true as the output from the complete.cases function called on the entire robot's data frame, which returns true for cases that have no missing values at all. And I'm keeping all of the columns, which is why I'm leaving the portion after the comma blank. And I'm just replacing the entire robot's data frame with this new smaller version of itself. So now robots has 500 observations of 10 variables. 3 of them are factors, transport, material, and color. And the rest of them are numeric variables, including the new legs variable that I created just a moment ago. Here's a summary of each variable in the dataset. Most notably, the transport variable refers to 256 robots with wheels and 244 with legs. We're going to be comparing those today. The price variable ranges from about $39 to about $169, with center somewhere around $100. And there are also three variables available that begin with rating dot something, which provide information about participants' subjective ratings of whether the robots are fun, practical, and cool, where lower scores indicate lower ratings of fun, practical, and cool, and higher scores indicate higher ratings. And that could be information that we use to try to help explain price differences between robots that have wheels and robots that have legs. Here's a correlation matrix of some of the key variables in the data frame, just illustrating that price seems to be positively associated with all three of these ratings, fun, practical, and cool, and also somewhat positively associated with the robot having legs. But the robots that have legs are more fun than the robots that don't have legs, whereas the robots with legs are slightly less practical than the robots that don't have legs. This code was my quick way of getting the variables that I wanted to use in this correlation matrix. You don't necessarily have to understand exactly what this code is doing for this class, but if you're curious about it, feel free to ask me. The example mediation hypothesis that I want to work with today involves using rating.fun as a mediator of the relationship between legs and price. So for this example, let's suppose that we have manipulated the method of transportation that the robots use, legs or wheels. When we've measured participants' ratings of how fun the robots are and how much they're willing to pay for the robots, so that we have causal evidence for the discrepancy in fun ratings between robots with legs and wheels and the discrepancy in price between the robots with legs and wheels. And our expectation is that people are going to perceive legs as more fun than wheels. And this may help explain why people pay more for robots with legs than they pay for robots with wheels. In other words, if we were going to draw the typical triangular path diagram to illustrate the mediation model, it might look sort of like this, with legs as the x variable, or the initial predictor variable, the feature of the robots that's expected to kick off this process, rating.fun in the position of the m variable, or the mediator, and price in the position of the final outcome variable. So let's revisit the three key regression models that are vital to understanding the process of statistical mediation analysis. First, there's a model that I'm calling here the total effect model. And here price is the response variable and transport is the sole predictor variable. This model allows us to capture the full discrepancy in price between robots with legs and robots with wheels. Then there's a model that I'm referring to as the A-path model. And here I have rating.fun as the response variable and transport as the predictor, which allows me to capture the full discrepancy in fun ratings between robots with legs and robots with wheels. These two models together will reveal the mean price difference between robots with legs and wheels and the mean fun difference between robots with legs and wheels. And finally, the B-path model is a regression model that has two predictors, transport and rating.fun, both predicting price. So in this model, I will be able to learn the magnitude of the association between fun and price adjusting for transport, and the magnitude of the association between transport and price adjusting for fun. Here's a summary of the total effect model. The mean difference in price between robots with legs and robots with wheels is $5.81. And the p-value is low, so we would refer to this price difference as statistically significant. Participants rated robots with legs as being significantly more expensive than robots with wheels. Here's a summary of the A-path model. And again, we have a positive and statistically significant slope. This illustrates that the rating of fun is almost a full scale point higher for the robots with legs than for the robots with wheels. And that discrepancy in perceived fun is also statistically significant. Finally, here's a summary of the B-path model. And this illustrates two things. First, that the discrepancy in price between robots with legs and robots with wheels is no longer statistically significant when we adjust for how different they are in how fun they are perceived to be. And second, that fun ratings are associated with higher price, adjusting for whether the robot has legs or wheels. So within robots with legs and within robots with wheels, we see an overall association between the robot being more fun and having a higher price, where each scale point of fun on a scale from 1 to 7 is associated with about $5.21 additional price. The typical triangular mediation diagram has 3 regression slopes in it, often labeled A, C prime, and B. And I can retrieve those slopes from the regression models that we just looked at by extracting the model coefficients from the model object, and then retrieving the coefficient that corresponds to a specific variable name. So the A path is the slope of transport legs from the model where transport legs is predicting fun. The C prime path is the slope of transport legs from the model where transport legs and fun are predicting price. And the B path is the slope of rating fun from that last model, this number right here. There's one other slope we're often interested in called C. This is the total effect of transport on price, and it comes from a separate regression model. This is the one that I call the total effect model. You've been taught that A times B equals C minus C prime. And here I'm illustrating that that's the case in this example. By taking the A slope and the B slope and multiplying them together, I get this number, 5.15, which is an estimate of the indirect effect of legs on price via fun. And C minus C prime comes out to exactly the same number, and it always will when you fit models like this. A times B is known as the indirect effect. C prime is known as the direct effect, and C is known as the total effect. If we take this fundamental theorem of statistical mediation analysis, A times B equals C minus C prime, and just add C prime to both sides, then we learn that A times B plus C prime is equal to C, which is another way of saying that the indirect effect plus the direct effect equals the total effect. And that's one reason why it's called the total effect. The mediation story emphasizes both A and B. A, that legs should cause higher fun ratings, and B, that fun ratings should be associated with price regardless of legs. We typically use bootstrapping to get a confidence interval for the indirect effect, the product of A and B. And I want to quickly illustrate what bootstrapping the indirect effect means before I carry it out using actual functions that you would use on a day-to-day basis for this kind of analysis. So for the sake of that illustration, I'm going to just generate 41 estimates of the indirect effect, 41 bootstrap samples with the indirect effect calculated in each of those bootstrap samples. This part of the explanation is going to use a tool in the R code called a for loop. And if you're taking the graduate statistics class in 2023, then I have not covered what a for loop is in R yet. And I'm not planning to cover it in detail in this class. So if that aspect of the following example loses you a little bit, don't worry about it too much. I'm setting up first a vector of missing values, 41 missing values called indirect effect estimates. And I'm going to fill in that vector one value at a time with 41 estimates of the indirect effect from 41 different bootstrap samples. And here's where the for loop begins. For I in 1:41 is just a way of telling R that I'm about to give it some additional instructions, and those additional instructions are to be repeated 41 times, where the variable I is replaced with the number 1, and then 2, and then 3, all the way up to 41. The first step of those instructions is to draw a bootstrap sample. There are 500 participants in the robots dataset that I'm working with right now, so I'm going to draw a sample of 500 of those participants, but I'm drawing it with replacement, so some of the participants will be duplicated and some will be omitted. The sample function allows me to accomplish this with the argument replace equals true. Next, I'm going to fit the 2 key regression models on this new subset of participants. Here I'm just calling them Model 1 and Model 2, although you could call them the A path model and the B path model if you want. Then I'm going to calculate the indirect effect from this particular bootstrap sample by extracting the slopes from these models. And I'm going to plug it directly into the vector of indirect effect estimates in position I. So I'm retrieving the transport leg slope from model 1 and the rating.fun slope from model 2, multiplying them together and assigning the result to the ith element of the indirect effect estimates vector. And finally, I end the for loop. And this is the point where all of this code executes. You can see that these plus signs that were present along the way indicated that R was not yet done receiving its instruction for what to do next, and it was waiting for me to finish. The closing curly bracket indicated when I was done. And now I can look at the 41 estimates. Here is that vector on its own. So the first bootstrap sample estimated the indirect effect at 5.6, and then 4.0, and then 4.6. It's more useful to look at them in order, so I'm going to sort them. And now I can see that the lowest indirect effect estimate came out to 3.4, and the highest one came out to 7.7, and all the rest fell in between that. And somewhere in the middle of this distribution of indirect effect estimates, the values will be quite close to the actual estimated indirect effect from the sample of all of the participants. In this case, the second lowest and second highest indirect effect estimates are like a 95% confidence interval because they encompass 95% of the estimates from the bootstrap samples. That's why I chose 41 estimates. So the 2.5th percentile estimate is this 3.726, and the 97.5th percentile estimate is this 7.513. Of course, 41 repetitions is nowhere near enough to get a good confidence interval. So when we do bootstrapping for real, we're going to use thousands of samples instead of just 41. But the basic premise is very similar. We're going to calculate different indirect effect estimates for each subset of participants that we're working with. And I use the phrase subset somewhat loosely because the bootstrap samples of participants are the same size as the actual sample of participants, but some of the participants are duplicated and others are omitted. And then, rather than simply using the 2.5th percentile and the 97.5th percentile directly from the set of all indirect effect estimates from all the bootstrap samples, we're just going to make a couple of adjustments to the resulting confidence interval to reduce its bias. What I did in this example is called a percentile confidence interval, which is pretty good on its own. But researchers will typically use some modifications of this percentile procedure, called bias-corrected or BC confidence intervals, or bias-corrected and accelerated or BCA confidence intervals. I'm not going to go into any detail about how those are calculated, except to say that they're generally accepted to be slight improvements on the percentile method, and so when the software offers you one of these options, you might as well take it.